Everyone. So in the last two classes we are discussing arrangement and selection without repetition and with repetition. In today's class we will discuss one special form which is distribution. To begin with, let us consider the following question, which says that how many ways are there to assign 100 diplomats to 5 continents? Think over it. So each diplomat has 5 choices. Yes, and in total there are 100 diplomats, so therefore you multiply 500 times, that gives you 5 raised to the power 100. The next one is how many ways 20 diplomats must be assigned to each continent. So in total 100 diplomats are there, then out of 100, let's say you give 20 to first continent, there remains 80, again you give 20, there remains 60, you give 20, there remains 40, you give 20, there remains 20, gives 20, which is same as P of 100, 20, 20, 20, 20 and 20. So if we see the distribution problem, then the problem of distributing are distinct objects are distinct as well as boxes are distinct, is equivalent to putting distinct objects in a row and stamping one of the n different box names to each object. So each box, by stamping one of the n different box names, so box name on each object, and then it is a problem of arrangement of the objects of length r out of n items with repetition, and that's why it is equivalent to n raised to the power r. And the other case is, if Ri object must go in box I, then there are P, R, R1, R2, Rn distributions. So two cases are there, and we will discuss the third case also with this problem, which says that there are 20 identical red sticks and 15 identical black sticks are there. In how many ways they can be distributed among 5 children? So if you see this problem, then this problem can be seen as distribution of 20 identical objects to 5 different boxes. Yes, and which can be done is into C r plus n minus 1. So 20 objects are there, 5 boxes are there, multiplied by 15 plus 5 minus 1 and 15. Since and is there, it means there are these two cases. We are not considering the sub cases, and multiplication principle will come into the picture. So you can see that in the previous case this identical word was not there. When we are talking of the diplomat, it has been used 100 different diplomats. So when different word was there, it was a problem of arrangement, and now this is a problem of selection. So distribution of distinct objects is arrangement, while identical object is about selection. So this is the standard table which we have discussed till now. So arrangement with no repetition, unlimited repetition and restricted repetition. Similarly, selection with no repetition and with repetition. So how many ways are there to distribute 4 identical oranges and 6 distinct apples into 5 different boxes? So one is the problem of arrangement, one is the problem of selection. So when we talk of the identical orange, then C r plus n minus 1, so 4 plus 5 minus 1 comma 4 multiplied by 5 raised to the power 6, because apples are distinct, so n raised to the power r. The next case says that how many ways the distribution can happen when each box get exactly 2 objects. Yes, so 5 boxes are there, each one has exactly 2 objects. Now the problem here is that all 10 objects are not identical. Yes, there are 4 identical oranges and 6 distinct apples. So we need to break down the problem into different cases. For example, there are 5 boxes, there are 2 oranges and remaining would have the apples. So it means 2 boxes have oranges which can be, so how do we select which boxes have oranges, because all boxes are distinct. So out of the 5 boxes we must select 2 boxes which should have oranges, so that the remaining boxes would have apples. And now all apples are distinct, which is a problem of arrangement. So total 6 apples are there, out of which 2, 2 and 2 goes into the remaining 3 boxes. The other case is 2 oranges, 1 orange, then 1 apple, then 2 apple and 2 apple. So it means there is only one box which need to be selected having 2 oranges, and out of the remaining 4 boxes there are 2 boxes need to be selected having 1 orange, and then the apples need to be distributed, so 2, 2, 1 and 1. And the third case is 4 boxes have 1, 1 oranges, so 5C4, and then there comes the apples, so 2, 1, 1, 1 and 1. Since these are the 3 sub cases, we add them to have the required answer. And in the problem it has been asked the fraction, so we divide it by the total number of the possibilities, that gives us the required fraction. So very interesting problem where we have used both the things, identical as well as distinct. Compute the number of the ways to distribute R identical balls into n distinct boxes, identical balls, distinct boxes, with at least one ball in each box. So think over it, there are n boxes, each box has one ball, so the remaining balls are R minus n. So R minus n to be distributed in n boxes, so plus n minus 1 and R minus n. Yes, this is, if you simplify it, is equal to R minus 1 and n minus 1. So there comes the simplification. So it's important to remember this formula, we may use it directly. Similarly, at least R1 balls in first box, R2 in second box and so on. So again you will see that in this case C R minus R1 minus R2 minus Rn plus n minus 1, and then R minus R1 minus Rn. So if you see this one, then it would be further simplified as C R minus R1 minus R2 minus Rn plus n minus 1 comma n minus 1. So two important formulas which we are going to use in the further questions. Very interesting question to think about. How many integer solutions are there, and xi are greater than or equal to 0, which means the positive integer solutions are there to the equation x1 plus x2 plus x3 plus x4 is equal to 12. Yes, now you need to put it as an arrangement or selection or distribution problem to solve it. So if we see it as a distribution problem, then we can say that there are 12 identical objects which need to be distributed in 4 boxes. For example, if x2 is equal to 3, it means to the box x2 we have put 3. If all have 3, so 3 plus 3 plus 3 plus 3 is equal to 12. So it means 12 objects need to be distributed in 4 boxes. How many solutions with xi greater than or equal to 1? So we just discussed it, the case to distribute R identical balls with at least one ball in each box, which is C R minus 1 and n minus 1. And the last one is C R minus R1 minus R2 and so on. So 12 minus 2 minus 2 minus 4 plus n minus 1, which is plus 4 minus 1, and n minus 1. Yes, so I have just used the formulas which we have discussed in the previous slide. So these equations which have the integer valued solutions are known as the Diophantine equations. Again, a very interesting question which says that how many arrangement of the letters, 5 vowels are there and 8 X are there, so that no two vowels can be consecutive. So vowels cannot be consecutive. It means that we should put at least one X between the vowels. So if 5 vowels are there, 1 2 3 4 5, so between them at least one X need to be put, but X can be before V, after V. This is the situation. It means that 4X has already been put and total 6 positions are there and X are identical. So it means that the remaining 4X need to be distributed in 6 boxes and 5 vowels need to be put. But now all vowels are distinct. It's not given, but we have to see it that they are distinct. It means that it can be P5, 5, which is 5 factorial. Yes. Now in this case, someone may give the another approach where total 13 letters are there, where 8X are similar. So total 13 factorial by 8 factorial possibilities, minus you take 2 vowels which are consecutive, so 5C2, because you choose 2 vowels out of 5, and you consider these 2 vowels as one letter. So now total 12 letters are there divided by 8. Is this approach correct? Think over it, and when you think over it, you will realize that when you choose 5C2, so for example AE comes and then X and then OU and the remaining comes. But when you choose OU, then X and AE, the same solution would get repeated. So that's why this would have the repetitions. So it has some extra solutions, and that's why this approach is not correct. What fractions of the binary sequences of length 10 with positive number of ones, zeros, and so on and so on? It means that if you think over it, then total 10 identical items are there which need to be distributed in 4 boxes, assuming that each box has at least one item. So C R minus 1, comma N minus 1. Okay, so quickly we can see that the equivalent form of selection with repetition, so it is same as distributing R identical objects into R distinct boxes, or it is equivalent to number of non-negative integer solutions to this equation. So that's all from today's class. Thank you very much.